The end of the 19th century was characterized by an unnatural confidence in scientists' knowledge of nature. John Trowbridge, the head of Harvard's physics department, dissuaded young, bright, science-minded students from pursuing physics. He gave them his word that, at the very least, they understood everything. Physics would advance because of more accurate measurements, in contrast to the discoveries in electricity and magnetism that defined the 19th century. Albert Michelson asserted that physics belongs in the sixth decimal place. Strangely enough, Michelson was one of the key experiment designers who foresaw the collapse of classical physics and signaled the arrival of Einstein's theory of special relativity. Before these grave misjudgments, physicists had seen phenomena that, when correctly interpreted, would pave the way for the quantum revolution and the current particle physics paradigm. Two phenomena provided crucial direction along the way. Phosphorescence and fluorescence are two of the first widely recognized sets of phenomena. Exposure to light and removing the light source trigger phosphorescence in a substance. Today's glow-in-the-dark paints are a wonderful example of phosphorescence. On the other hand, fluorescence is different. Fluorescent materials only emit light when illuminated by another light source, but the color is different. Today's black light posters offer well-known illustrations of fluorescence. Though they were not fully understood, both phenomena were present and important in the early moments of epiphany, when some lucky scientists realized they had made a new discovery. An ongoing fascination with electricity and its workings led to another fascinating phenomenon. Sparks captivated scientists early in the history of electricity research. William Watson, Benjamin Franklin's friend, once said in the 1740s that watching electricity move through a dark room was the most delightful thing to see. One inquiry focused on the impact of the composition and gas pressure that divided the spark's two sides. A spark shoots through the air when you step onto a doorknob and shuffle your feet. Scientists could produce pure samples of various gases, including nitrogen, hydrogen, and oxygen, by the first part of the 1800s. Researchers studied pure gases to determine the amount of electricity required to ignite each gas. To achieve this, a glass blower was used to create a flask with two gas flow apertures. Connecting a strong battery to each end of the two plates produced sparks. The researchers then introduced a gas, such as hydrogen, into the flask until they completely removed the air. The problem was that it took a long time and a lot of hydrogen gas to completely replace the air. We needed a way to drain the air and bleed precisely the right amount of gas. Scientists predict that a glowing purplish snake, similar to the eye of the storm globes available today, will eventually replace the spark. Heinrich Geissler invented the mercury vacuum pump in 1855, simplifying the process of extracting air from a glass flask for experimenters. In or around 1875, William Crookes constructed a tube, later known as the Crookes tube, to precisely measure the voltage required to create a spark between the plates. But as he raised the voltage, he realized that he could see an electrical current in his circuit before a full-blown spark existed. The plates weren't in contact, so if one pumped for a long enough period, the electricity would have to pass through the gas or vacuum. He could only measure this tiny current flow with precise instruments, since gas and vacuum were considered insulators rather than conductors. Furthermore, he observed the flow of electricity through the gas as it released light, but the source of the light was not immediately clear. Following his investigation, Crookes deduced that the movement of electricity could be from the cathode, the negative side of the battery, to the anode, the positive side. After that, in 1876, Crookes's contemporaries modified his tube by making a small hole in the plate connected to the positive side of the battery to better inspect its properties. Eugen Goldstein, a German physicist who lived during Crookes's most active research period, had named this flow cathode rays. Cathode rays could enter this hole and strike the glass vessel's far end. This advancement in Crookes's design allowed cathode ray research to begin earnestly. Researchers found that when the cathode rays struck the end of the glass vessel, they could produce a considerable amount of heat and travel in straight lines. Crookes was aware that past research had demonstrated that charged particles would travel in a circle in the presence of a magnetic field. After observing the deflection of cathode rays in a magnetic field, Crookes concluded that cathode rays were a type of electricity. Applying a phosphorescent substance, such as zinc sulfide, to the end of the glass vessel using the upgraded Crookes tube shows how cathode rays cause the zinc sulfide to glow. These early experiments will help the curious reader identify the source of their computer monitor or television, a CRT or cathode ray tube. Crookes thought he had found a fourth state of matter, which he named radiant matter. Nevertheless, his explanation of cathode rays was false, because his theoretical or explanatory abilities needed to match his considerable experimental skills. Fortunately, Crookes lived until 1919, when they witnessed some of the remarkable offshoots of the Crookes tube. His outstanding contributions to various scientific fields earned him the Order of Merit in 1910 and a knighthood in 1897. Apart from developing the apparatus that evolved into the computer monitor and television, we are familiar with Crookes' radiometer invention. The radiometer is a clear, light bulb-shaped glass device with 4 vanes painted black or white on alternate sides. The vanes spin when they're close to a source of light. We'll talk about Crookes' discovery of radioactivity, which he studied later in life. He found that P particles, or the particles expelled from radioactive materials, such as uranium and radium, would cause a tiny flash of light to occur with each impact when forced against zinc sulfide. This technique will be used again when we discover the nature of the atom. Despite having nothing to do with particle physics, Crookes' discoveries indirectly paved the way for the amazing discoveries of the early 20th century. Crookes tubes are no longer for sale for reasons that will become clear shortly. Researchers studied cathode rays long after their discovery. While many researchers focused their energies on studying the luminous properties of light, a young Heinrich Hertz assistant made an amazing discovery in 1892. Philip Lenard applied a very thin layer of aluminum to the end of a Crookes tube. To everyone's surprise, the cathode rays could penetrate the aluminum. This demonstrated that cathode rays, the glowing characteristics that piqued the interest of most investigators, could pass through a solid metal wall, an opaque surface. Very enigmatic. There's no doubt that this result was a crucial piece in the puzzle, even though Lenard's later strong support of the Nazi Party embarrassed his scientific colleagues. After a few years, things became very intriguing. Wilhelm Conrad Röntgen was an average physics professor. His work was notable not so much for his remarkable insights, but also for his meticulous attention to detail. By 1895, Röntgen had transferred 4 times within the German university system, indicating that he was not likely to advance to higher ranks. It's helpful to point out that the American university system is unlike the German one, particularly during that particular era. Each university had only 1, or, at most, a few professors for each subject. In the American system, assistants to the professors were junior professors, but they had the same status in the German system. The senior professor exercised considerable control over his subordinates while running his laboratory or institute. Some of my more senior German colleagues recount stories of having their thesis professor's car washed and the lawn mowed. Röntgen lacked the poise required to become head of a major physics institute and advanced to the top of the German university system. However, Röntgen's work was of the highest caliber, and in 1895 he held the positions of rector and professor of physics at the University of Würzburg. Alone in his lab that November 8th evening, Röntgen tried to make sense of Lenard's observation that cathode rays could pass through a thick metal wall. Röntgen positioned a barium-platinum cyanide-covered screen approximately 6 feet from the tip of his cathode tube. Enough light was available to impede Röntgen's investigation of dim cathode rays glowing in glass tubes full of gas, even though the night was dark and the lighting was not as excellent as today. To alleviate the problem, Röntgen covered his tube with an opaque black box. In a dimly lit corner of the lab, Röntgen had the bright idea to aim his tube at the screen. Röntgen stopped studying and rubbed his fatigued eyes when he noticed something strange. The screen was glowing. The glow vanished when he switched off his tube's electricity. As any responsible physicist would, Röntgen replied. He said, "Huh," or whatever the German word is. As he pried the screen open and closed, he noticed a slight shift in the glowing spot's size, similar to the movement of a piece of paper towards or away from a flashlight. He flipped the screen over. It continued to glow. When he averted the tube, the glow vanished. He replaced the tube with a few different Crookes tubes. The radiation persisted. He then began sandwiching different objects between the tube and the screen, including paper, pens, books, and other items. He discovered that most objects continued to glow. The source of the glow appeared transparent. In fact, he had to put relatively thick metal objects between the tube and the screen to stop the glow. However, he noticed an intriguing effect when he placed his hand between the tube and the screen. Much of his hand was also transparent, though some areas did not glow. He knew he was looking at his bones when he looked closely at the dark areas. Having worked with cathode rays for a while, Röntgen knew they lacked the necessary characteristics to produce the phenomenon he saw. It would be much easier to stop cathode radiation. And that's when Röntgen realized he was seeing something completely different. He gave his discovery the moniker X-rays, which is still in use today. We remember that Röntgen wasn't a showy guy. Instead, he was very cautious. He didn't immediately build a commercial product out of his invention or get in touch with the media. Rather, he concentrated on investigating the characteristics of X-rays. He even devised a method for filming his photos. Ultimately, he sent copies of his report and advertisement photos of his hand's bones to numerous prestigious European laboratories on January 1st, 1896. Henri Becquerel was among the recipients, and on January 20th, 1896, he forwarded the letter to the French Academy of Science. Reprinted in Science, Nature, and other prestigious journals, this paper went viral in Europe. His work was promptly duplicated by other scientists. Roger received hundreds of letters and telegrams of congratulations from worldwide. The news spread quickly, as evidenced by the February 9th New York Times story, "The Wizard of New Jersey, Thomas Edison, will try to photograph the skeleton of a human head next week." Despite Edison's failure, there was obviously excitement everywhere. Successful lawsuits against doctors demonstrated how quickly the risks of X-rays harming living tissue became apparent. Some things never change. They adopted rather contemporary safety measures early on. The medical community promptly recognized the enormous practical value of the discovery. Little Eddie McCarthy of Dartmouth, New Hampshire, had his broken arm set within 3 weeks of the discovery being announced in Paris after the doctors first examined the break with an X-ray. The phenomenon led to over 1,000 papers published within a year. Naturally, only some were as excited to hear the discovery news. A major clothing manufacturer quickly took advantage of some public concerns and advertised X-ray-proof women's clothing. A London newspaper wrote, "On the revolting indecency of this, there is no need to dwell, and it calls for legislative restrictions of the severest kind." Regarding the phenomenon he had described, Röntgen only delivered one talk. He addressed the Physical Medical Society at the University of Würzburg about a month after he had sent out his letters to thunderous applause. Röntgen published only 2 more X-ray papers before mysteriously switching to other areas of study. After relocating to Munich in 1900 and becoming director of the Institute of Experimental Physics, his career improved. Röntgen was the first recipient of the Nobel Prize in 1901, and he set a high bar for others. Due to Röntgen's retiring nature, he managed to elude giving the obligatory public lecture that comes with receiving a prize by scheming out of Stockholm. He could replace the mandatory talk with his earlier lecture at Würzburg, using some legal legerdemain. Present recipients must deliver a lecture to the Swedish Academy of Sciences. Regretfully, Röntgen did not profit from his discovery. "There's a war on, you know," he said, referring to the funding cut for his institute during World War I. He passed away at 73 during the inflationary Weimar period that followed the two wars. Röntgen's discovery of X-rays thrilled all practicing physicians at the time. On the other hand, it motivated one person to pursue unanticipated paths in their future research. Following the announcement of the discovery of X-rays, Henri Becquerel, a French Academy of Sciences member, attended numerous conferences. Becquerel, like his father and grandfather, was a French physicist. Having studied phosphorescence with his father, Becquerel had an intuition after witnessing numerous colleagues darken photographic plates using different Crookes tubes. Phosphorescence might have caused the X-rays. Becquerel had been doing little research for a while, but his hunch excited him. His family had been fascinated by the phenomenon, and he had a sizable collection of rocks and wood that would glow in the dark after a suitable period in the sun to charge up. When he returned to his lab, he took a few phosphorescent materials and set them on top of a photographic plate in a dark room after activating them in the sun. He expected phosphorescence to darken the plate and release X-rays. After numerous trials yielding negative outcomes, the situation appeared hopeless. Then, for the chemically inclined, he chose to try crystalline lamellas of the double sulfate of potassium and uranium. We'll refer to this as uranium salt. This specific material glows when exposed to ultraviolet light. Becquerel placed the photographic plate and uranium salt in an opaque holder. He left the plate out in the sun for roughly half a day. Becquerel placed a second identical photographic plate, devoid of uranium salts, carefully next to the first one. This control, as it's known, would replicate the effects of prolonged exposure of a shielded photographic plate to sunlight. He discovered the plate remained unchanged even after being developed without uranium salts. However, the salt's outline was visible when he exposed the photographic plate to the uranium salts. He had evidence that phosphorescence produced X-rays. Or did he? Becquerel, a meticulous experimenter, conducted several additional tests. By reflecting sunlight through a mirror and then passing it through a prism, he charged up the uranium salts. The uranium salts fogged the photographic plate. He discovered that even though he could see the image of the cross on the photographic plate, the plate remained exposed, even beneath the cross, suggesting that the copper only partially blocked the unknown rays. He then placed a thin copper plate in the shape of a cross between the photographic plate and the uranium salts, allowing the copper to block the X-rays. When he conducted the tests again, using a thinner copper cross, he discovered that it blocked the rays even less. Then, Becquerel experienced some extraordinarily fortunate events that did not appear favorable. On February 26, 1896, he made photographic plates and set them in the sun. Fortunately, the day was mostly overcast, meaning he didn't see much sunlight during the week. He stored the entire device in a drawer for later use. The uranium salts would not phosphoresce in the dark, so he anticipated the plates would be nearly unfogged. But he expected there would be some fogging because of the sunlight. Rather than make future experiments more difficult by reusing these plates, he developed them on March 1st. He was surprised to see how foggy the photographic plates were. Very strange. It seemed that visible phosphorescence was not the cause, since Becquerel knew that the phosphorescence of these specific uranium salts persisted for about 1/10 of a second. In his first paper to the French Academy, he observed a behavior resembling that of Röntgen's X-rays, and he conjectured that sunlight might have activated the X-rays for a far longer period than the visible phosphorescence. Becquerel released a second paper at the end of May that went into more detail about his discovery. He left some uranium salts in the dark from March 3rd to May 3rd, giving the invisible phosphorescence time to fade. He discovered that the uranium salt's capacity to cause a photographic plate to fog had not diminished. He also conducted more experiments with different uranium salts, some of which showed no phosphorescent behavior. He surmised that a disk of pure uranium metal would further obscure the plates, a notion he later proved after realizing that uranium, not phosphorescence, was the crucial element. By the end of the summer, he thought he had found something different, an invisible phosphorescence connected to uranium. By year's end, he had demonstrated that the rays he had found had many distinct properties upon closer inspection, despite their apparent similarities to Roentgen's. Even though he had not yet invented the term, he discovered radioactivity. To better understand radioactivity, one must take into account the contributions of others. Even a century after its discovery, the first is still widely recognized. On November 7, 1867, Maria Sklodowska was born into a family of educators. Teaching was no more profitable in the 19th century than it is today. Maria was a very intelligent young lady who dreamed of becoming a scientist, which was practically unheard of then. Maria's inability to afford college compelled her to tutor the children of wealthy individuals. She lived a frugal life, sending all her extra money to her sister Bronia, who studied medicine in Paris, because she felt a strong sense of duty to her family. The plan was for her to pay the favor forward after Bronia became well known in her medical field. Thus, Maria arrived in Paris in 1891. The amount of credits needed to earn a degree then differed from what it is now. Maria studied for a while before easily passing her physics degree and moving on to study mathematics. She married Pierre Curie, a young scientist renowned for his contributions to magnetism and crystallography, in 1895. Maria Sklodowska, who went by the name Marie Curie after her marriage, decided to pursue a doctorate in physics in 1897. Roentgen and Becquerel's recent discoveries have demonstrated how exciting this era was. In contrast to the more easily manipulated X-rays and their progenitors, cathode rays, not many people attempted to understand Becquerel rays, despite Becquerel's recent work. This was perfect for Marie because it would save her time and allow her to focus on her experiments instead of sifting through a large body of literature. Numerous experiments have explored a topic, yielding straightforward outcomes in numerous written papers. This further complicates future discoveries. Becquerel rays had a lesser profile, so her chances of discovering something intriguing were higher. She undertook an extremely impressive program to understand the Becquerel rays. She examined uranium in all its forms: powdered, solid, wet, dry, or compound. She determined the amount of uranium in each compound using Pierre's and her considerable chemical skills, then compared the results to an equivalent amount of solid uranium. She found that only uranium mattered in every situation. In April 1898, she tested every other known element at the time and found that thorium and uranium could cause a plate to fog. Naturally, the question remained whether uranium and thorium radiation were identical. Curie enhanced his research on radioactivity with a new device. As anyone who has looked at an exposed piece of film will attest, it takes work to precisely determine its exposure level. Light is light, and darkness is darkness. Using an electroscope, Becquerel demonstrated that his rays made air conductive. Pierre Curie and his elder brother, Jacques, created a more sensitive electrometer in 1886 to detect minuscule electrical currents in the atmosphere. The concept is straightforward. A single plate connects to a battery. Air keeps the plates apart. The air becomes slightly conductive when we place the radioactive material close to the plates. The electroscope measures the tiny electrical currents that pass through the air. When radioactive substances increase, the air becomes more conductive and detects a higher current. Curie's laboratory was a terrible place to conduct experiments because it was a damp potato cellar. she could still make precise and repeatable measurements despite the dampness in the air, which made it conducive and directly competed with the effect she was trying to measure. We had discovered the radioactivity of thorium. During this period, two important events happened, and Marie Curie coined the term radioactivity after the Latin word for ray. Initially, Pierre left his work on crystals to join Marie after realizing she was researching something novel. Second, there was a serious consideration of what was causing the radioactivity. Both Becquerel and Curie demonstrated the radioactivity of pure uranium and uranium salts, indicating that the radioactivity of uranium did not stem from the chemical bonds of the salts associated with it. Chemistry studies of thorium led to the same conclusion. Of course, this led to an extremely interesting question. At the time, people considered the atoms of the elements to be fundamental. Each atom was a point devoid of any internal organization. Its mass and chemical behavior were its primary characteristics. It is now known that two elements behave differently. What the heck is it about thorium and uranium that makes it radioactive? Was the question on everyone's mind. And Curie quickly contributed to the confusion with her deductions and later discoveries. She discovered that pitchblende and chalcolite, two common uranium ores, were even more radioactive than uranium. Marie conjectured that previously unidentified, even more hazardous elements were responsible for the radioactivity of these minerals. As usual, she worked diligently to isolate the two new elements. She isolated two extremely radioactive samples after arduous and time-consuming work. In the first sample, bismuth predominated, whereas barium did in the second. She surmised that each sample contained a mixture of the predominant, radioactively inert element and a trace amount of a chemically related, highly radioactive element, because neither barium nor bismuth were radioactive. This was the same as Mendeleev's table, discussed in Chapter 1. The Curies published a paper in June 1898, announcing the discovery of a new element named polonium, named after Marie's birth country. The only difference between polonium and bismuth's chemical makeup was that the former was radioactive. They declared the discovery of radium, the radioactive analog of barium, in December of that year. Despite having very different chemical properties, both new elements were radioactive. The Pantheon welcomed two new radioactive elements. After observation, purified samples of these novel elements were necessary. After 3 years of processing a ton of pitchblende, she could extract 1/10 of a gram of radium chloride, or about the mass of a paperclip. Polonium degrades in roughly 3 months, so she could never isolate it. Thus, it degraded even faster while she was separating it. In 1903, the committee proposed Pierre Curie and Henri Becquerel for the Nobel Prize in recognition of their discoveries and analyses of radioactivity. Magnus Gösta Mittag-Leffler, a Swedish mathematician and pioneer of women scientists, was a nominating committee member, and he wrote to Pierre to inform him of this injustice. Pierre responded with outstanding elegance, stating that it would be incredibly unjust to award a Nobel Prize for radioactivity research to anyone other than Marie. He composed, "If anyone seriously considers me for the Nobel Prize, I want to be considered, along with Madame Curie, for our work on radioactive bodies." The Nobel Prize in Physics went to the Curies and Becquerel in December 1903, the year Marie earned her doctorate, for their discoveries in radioactivity. Since the Chemistry Nominating Committee also wanted to consider Marie Curie for the Nobel Prize in Chemistry, they insisted that the physics citation leave out the mention of radium's discovery. She received that award in 1911. Becquerel and the Curies have had a profound effect on humanity. The Curies also left behind their daughter Irène, who shared a laboratory with her mother and her husband, Frédéric Joliot. 1935, the couple received their Nobel Prize for discovering artificially induced radioactivity. Naturally, the question of whether radioactivity was a phenomenon of waves or particle emission persisted even after Becquerel's demonstration that it differed from X-rays. In June 1903, a scientist from New Zealand who was in Paris attended Marie's doctorate award celebration, making her the first woman to receive such an honor in France. Ernest Rutherford, the scientist in question, had personally studied radioactivity. In 1899, Rutherford discovered two very different forms of radioactivity in uranium. Rutherford accomplished this by subjecting the radiation to an electric and magnetic field and measuring the ray's deviation. The strong bending of the magnetic field indicated the presence of a negatively charged component. We named this type of radiation as beta radiation. Furthermore, a magnetic field did not alter the course of another kind of radiation, alpha radiation. A closer inspection revealed a tiny deflection that suggested a positively charged particle. The particle's extreme weight in alpha radiation eventually explained the tiny deflection. Paul Villard of the École Normale Supérieure in Paris, France, discovered gamma rays in 1900. Villard identified a radiation component that was independent of electrical and magnetic fields. Investigative work revealed that these rays, unlike another phenomenon called X-rays, entered matter differently. Ernest Rutherford made a very remarkable discovery in 1900. He saw that as time went on, thorium's radioactivity dropped. This implied that radioactivity might disappear. Since uranium radiation appeared constant, such an observation was highly suspicious. Together with chemist Frederick Soddy, Rutherford developed a crucial mechanism in Montreal, Canada, to account for the decline of thorium radiation. They thought converting one element into another was the ultimate definition of radioactivity. Their theory suggested that atoms could not change, which meant that the era of the unchanging atomic element was ending. Perhaps even more ironic was their success in creating gold through a process that 19th century chemists and those earlier Renaissance alchemists had proven impossible. The August 1903 issue of Scientific American summed up the scientists' dismay. The conundrum of what to do with the recently discovered radioactive substances confounds every rational physicist. They are incompatible with our well-established and harmonious chemical system. They threaten the atomic theory we have revered for almost a century. Previously believed to be basic forms of primordial matter, the elements now proudly declare themselves tiny astronomical systems of rotating units of matter. Though they seemed more like scientific moonshine than sober thought, Sir Oliver Lodge and Lord Kelvin accepted the new doctrines. The multiplicity of different rays was a concern, even though the unchangeability of elements, the fundamental tenet of 19th century physics and chemistry, was now in question. Alpha, beta, gamma, and X-rays were all present. Cathode and canal rays were also present, an interesting but unimportant byproduct of cathode rays. Research by Rutherford, Becquerel, and others showed that gamma and X-rays are immune to the effects of electric and magnetic fields. Researchers have demonstrated that alpha and canal rays are positively charged particles with a comparatively large mass. Ultimately, cathode and beta radiation exhibited characteristics of negatively charged particles. Additionally, after examining their capacity to pass through materials, cathode and beta rays appeared uncannily alike. An interpreter was required to sort through the confusion. To fully understand the essence of things, we must delve into the life of Joseph John Thomson, known as JJ, from 1897 to the present. The electron's discovery. One of the most renowned scientists in Britain, J.J. Thomson, oversaw the Cavendish Laboratory at the University of Cambridge. He was interested in cathode rays and applied his exceptional experimental abilities to investigate this issue. J.A. was born on December 18, 1856, into a homemaker and book publisher family. Despite having typical childhood experiences, he showed an early aptitude for technical subjects during his early years. His parents sent him to Owens College, Manchester University, when he was 14. His dad had chosen an engineering company where JJ would someday become an apprentice. Thomson would continue his engineering studies while awaiting an engineering apprentice position at the selected company. Thomson's father passed away when he was 16. The price his family had agreed upon for the engineering firm to hire him was suddenly an insurmountable obstacle. His mother broke the bad news to him, saying that his dreams of becoming an engineer were no longer feasible and that JJ relocated to Cambridge's Trinity College to pursue additional engineering studies. Once there, he discovered that mathematics was his true passion. The rigid student ranking system played a significant role in shaping decisions about future career paths in 1876. Under such a system, students naturally competed fiercely, with Thomson placing second in his class behind the future famous theoretical physicist Joseph Lamore. 1880 saw JJ start working for Lord Rayleigh, the laboratory's director at the time, at Cavendish Laboratory. To the surprise of many, Thomson took over as laboratory director upon Rayleigh's retirement in 1884. Not everyone was thrilled about Cavendish's choice of a relatively unknown scientist as his first two directors, the illustrious Maxwell and Rayleigh. One college tutor said that the appointment of men as professors marked a major shift. "Pardon me if I have done something wrong by not writing to you before to wish you happiness and success as professor. The news of your election was too delightful a surprise to allow me to do so," wrote Glazebrook, a demonstrator at the laboratory, in a letter to Thomson. Despite these misgivings, Thomson's selection as Cavendish director was wise. Under his direction, scientists conducted incredibly fascinating investigations into the nature of atoms and electricity. Numerous of his protégés demonstrated their value by producing important discoveries and achieving prominent positions across Europe. In the end, Thomson elected 27 people as Fellows of the Royal Society and gave the Nobel Prize to 7 people who started their careers at Cavendish. Thomson was not very good at laboratory work, but he was excellent at interpreting the significance of the experiment's findings. H.F. A young professor named Thomson had an assistant named Newell who wrote, "JJ was very awkward with his fingers and I found it necessary to not encourage him to handle the instruments, but he was very helpful in explaining how things should go." Young Rose Paget, one of the first female students to be allowed to study advanced physics at Cambridge, was one of Thomson's many pupils. After graduating from Cavendish in 1889, Rose experimented with soap bubble vibrations. On January 22, 1890, she and JJ tied the knot and gave birth to 2 children. George Paget Thomson, the eldest, continued his father's scientific career and received the 1937 Nobel Prize in Physics. Joan Paget Thomson, their daughter, was devoted to her father and traveled with him often. When JJ took over as director of Cavendish Laboratory at that time, Thomson initiated an experimental program to gain a deeper understanding of the nature of electricity. Understanding cathode rays piqued his curiosity, as evidenced by his 1893 essay, "There is no other branch of physics that awards us so promising an opportunity of penetrating the secret of electricity." Remember, a vacuum pump created cathode rays when it removed most of the air from 2 electrodes in a glass tube. If the air pressure was suitable, a high voltage between the electrodes would cause the remaining air to conduct. As the air entered, it would glow like a purplish snake, writhing. The gas fluoresced due to cathode rays, which moved from the cathode, the negative electrode, to the anode, the positive electrode. When the cathode rays strike the glass envelope, the glass will sparkle. The study of cathode rays got serious with the invention of Crookes tubes, discussed earlier, and other similar designs. Magnets influenced them, but electric fields did not. The magnets caused the glass tube to heat up. They could also pass through a thin layer of metal and produce X-rays. What are these cathode rays, specifically? Indeed, numerous theories exist. British physicists generally believed that cathode rays were particles. The question that remained was, particles of what? Because cathode rays could charge up an electroscope, Jean Perrin had demonstrated that they carried electricity. One theory suggests that cathode rays release negatively charged atoms from the cathode. If this is the case, altering the cathode's metal would alter the cathode ray's nature, because different elements are known to have different masses. On the other hand, another theory holds that the cathode rays themselves did not carry any charge, but allowed charge to flow. This theory resembles a river filled with fish and water. Although they are not the same, they share some similarities and travel in the same direction. German physicists had an alternative perspective. Heinrich Hertz discovered that an electric field should deflect cathode rays like that of a magnet, since cathode rays are known to carry an electrical charge. He positioned two plates and created a strong electrical field between them, separating them by the gap the cathode rays traveled through. If it is electrical, the electric field should deflect the cathode rays. The experiment showed that Hertz's electric field had no effect on the direction of the cathode rays. The results of this experiment unequivocally demonstrated that cathode rays were not inherently electrical. Philippe Lenard, Hertz's pupil, had blocked the cathode's path with a thin aluminum foil. We remembered that the light passed through the foil in a previous conversation. The model proposed that the cathode rays vibrated the foil, which in turn vibrated the space beyond, allowing the cathode rays to pass through the metal. Talking to a drummer was an analogy. As the drumhead vibrates, the sound travels to the opposite side. The most popular answer to what was vibrating was that the ether was vibrating. People once believed that the ether conducted light vibrations. Cathode rays, therefore, were a type of light. However, cathode rays, not a magnetic field, affect light. Ha ha. It makes sense why there has been so much uncertainty about the nature of cathode rays. 1897, John J. Thomson said, "We hold the most diverse opinions as to these rays." It would seem apparent that it would be simple to discern between these different points of view, but practical experience suggests otherwise. Emil Vickert made an intriguing measurement in 1897. He could measure the mass-to-charge ratio, or ME ratio, for all the atomic elements. He found that hydrogen had the lowest ratio of all elements, so cathode rays' electrical charge would be 1,000 times greater if they had the same mass as hydrogen, and their mass would be 1,000 times smaller. Given that the result was expressed as a ratio, entering this bewildering mess with a team of capable aides, J.J. Thomson carried out 3 painstaking experiments to illuminate the subject and alter history. First, he changed an experiment done in 1895 by Jean Perrin that suggested cathode rays were negatively charged particles. An alternative way to look at Perrin's experiment was to say that cathode rays and negatively charged particles moved in the same direction, but had nothing to do with each other. Perrin had put an apparatus meant to measure electricity in the path of cathode rays and recorded the presence of electrolytes. J.J. added an external magnet, which pushed the cathode rays away from the apparatus. While this experiment did not totally rule out the cathode rays and electricity go in the same direction but are different hypothesis, it did provide very suggestive evidence that cathode rays and negatively charged particles were identical. He found that electricity always accompanied the cathode rays. If the cathode rays hit the electricity measuring device, it generates electricity. Hertz discovered that an electric field could not deflect cathode rays, contradicting the theory that cathode rays were negatively charged particles. But J.J. made a very smart observation. An electric field can push a charged particle away from it as long as it is not blocked from the field by something like a copper tube or mesh. This led him to develop a smart theory, since cathode rays make the gas conduct electricity. He thought that the electrically charged residual gas would shield the cathode rays from the effects of an outside electrical field. By conventional means, cathode rays could pass through an electric field onto a screen coated with a fluorescent material, to which a ruler had been applied to measure deviation. The cathode rays traveled in a straight line without an electric field, producing a bright spot in the center of the screen, but upon applying an electric field, the spot moved. JJ's explanation of why Hertz could not detect a deflection turned out to be accurate. And JJ provided an important response to the argument that cathode rays could not be electrically charged particles. Thomson's third experiment could only have been carried out if the experiment had been successful. This experiment involved measuring the speed of cathode rays, which, like light, had to travel at the speed of light, and verifying Richet's previous measurement of the mass-to-charge ratio of cathode rays. His method was based on two physics facts. First, magnetic forces are proportional to velocity. Second, if electric and magnetic fields are arranged to deflect a moving charged object in opposite directions, their respective strengths can be precisely cancelled. Once this is achieved, the particle's velocity can be calculated with ease. Modern laboratory demonstrations use this method. Thomson's original paper states that, although his approach is similar, it could have been more elegant. The experiment showed a significantly lower cathode ray velocity than light's, indicating that cathode rays could not be solely a light-induced phenomenon. Thomson's first result supported Richet's findings. However, cognizant that perhaps cathode rays were atoms of elements from the cathode or gas that had picked up an electric charge, he repeated the experiment with various gases and used different metals to construct his electrodes. He found the mass-to-charge ratio was the same in all cases, suggesting that the material making up the electrodes or surrounding gas didn't matter. In fairness, heavier atoms could pick up more charge. Recall that all he measured was a ratio. But he felt this was not the case. Ultimately, once the speed of the particles was known, the third experiment could easily determine the mass-to-charge of the cathode rays, although to see how obvious this is would require a brief excursion into mathematics. When Thomson saw that his mass-to-charge ratio was about 1,000 times smaller than that of any known element, and that this measurement was independent of the materials used to make it, he sat and thought, what could explain the multitude of properties he and others measured? He concluded that he saw something entirely new and wrote his seminal paper in 1897. These calculations show that the value of Ma is independent of the gas's nature, and that, when compared to the value 10⁴, the smallest value of this quantity that has ever been measured, and the value for the hydrogen atom during electrolysis, it is minuscule. Consequently, Me for the carriers of electricity in the cathode rays is small compared to its electrolysis value. We can attribute this smallness of Me to either the largeness of E, the smallness of M, or the combination of both. Then, Thomson reviews Leonard's results, which implied that very low-mass cathode rays were most likely. He does not go so far as to call this work definitive, presumably because he thought it necessary to directly measure the mass or charge of cathode rays. J.J. Thomson made an extraordinary announcement in the Great Lecture Hall of the Royal Institute of Great Britain, informing the crowd that he had discovered a particle part of an atom. All educated people knew that atoms were the smallest particles of an element, lacking any internal structure. Thomson was telling them that this wasn't true. Atoms had structure. On Friday, April 30th, 1897, J.J. lectured his colleagues and some of London's better people, who had gathered to hear what was new in science. Many chemists regard the constitution of the chemical element as the best explanation for the facts. In this view, the atoms of the various chemical elements are aggregates of the same kind. Prout proposed this hypothesis, positing that the atoms of the various elements are hydrogen atoms. However, this exact form of the hypothesis is not tenable. We find something compatible with this hypothesis if we substitute hydrogen with an unidentified primordial substance, X. Sir Norman Lockyer has recently supported this hypothesis based on his studies of stellar spectra. They will behave exactly like cathode rays if the strong electric field close to the cathode breaks up, separates the gas molecules into primitive atoms or corpuscles, and charges them with electricity before launching them from the cathode. Thus, this lecture marked the beginning of the modern era of particle physics for many scientists and historians. Despite his initial disagreement with his colleagues, Thomson called his discovery corpuscles. While most were skeptical of his claims, a notable audience member later informed Thomson that he believed Thomson was exaggerating. Evidence soon accumulated, and physicists began referring to the new particles as electron, a term that G. Johnstone Stoney coined in 1891 to describe the smallest unit of charge found in an experiment that passed current through chemicals. Thomson did not use the term electron for over 20 years. Even though Thomson had measured the mass-to-charge ratio, he could only say a little about both independently. 2 years later, however, he demonstrated that the charge of one of his corpuscles was roughly equal to that of a hydrogen ion. This led to the realization that the mass of an electron was extremely small. Current measurements put it at a mere 1/1886 of a hydrogen atom. The electron then became a very light component of all atoms, each carrying the same charge as an ion. Thomson received the 1906 Nobel Prize in Physics for his research into the discharge of electricity in gases. He received a knighthood in 1908 and the Order of Merit in 1912.